Hi, today we want to focus on word embeddings again. So we have already worked with word embeddings and seen how we can use word embeddings in machine learning models in a way that the embeddings are trained on the fly during the machine learning process. There is another class of word embeddings. So if you talk about word embeddings, what we mean is just that we have vector space representation for our words. So, for example, each word might be represented as a vector in a 300-dimensional vector space. Instead of training these words on the fly, there is a second approach, mostly known by the name Word2Vec. And there the idea is that the vector space is trained separately from the model in a way that words that are in the same context will move very close together in the vector space. And we have not seen yet how we can train such a Word2Vec vector space. And there are different models and different ways to train Word2Vec. Still, I think the most common model is the so-called SIBO model, but this is not a deep learning model or a neural network model. It's a model based on logistic regression. Nevertheless, it's very good, it's very fast, but we want to integrate it in neural networks. And there are two different approaches to do this. One is the so-called softmax approach, and the other is the Skipgram approach. In the softmax approach, the idea is that we have pairs, word pairs, a word and then another word that is in the context to this word. And given the first word as an input, then you have to build a model with a number of neurons adequate to the vector space that you want to create. So if you want to have 300 dimensions in your vector space, you will have 300 neurons. And you try to predict for each word, is this a context word or not? This works, but it's very computational intense. In the end, after the model is trained, you just store the weights of your layer, and these weights then are your Word2Vec representations. But there is a second approach that is much faster, but it's quite complicated to implement it. And this is nice for us because it shows us a new feature of the whole TensorFlow and Keras architecture. Up to now, we just worked with the Keras sequential API. This means that we could stack layer on layer in a model. But you can do other things with Keras and TensorFlow as well. It's a functional API, and this means that you can create more complex network architectures. And this is what we will do for this Skipgram approach. And what I'm going to show you now is based mainly on this tutorial. This is taken from Adventures in Machine Learning. And here you can see the architecture of the Skipgram model with negative sampling. So the idea is we have two inputs, a target word and a context word. And in the end, we just want to decide, is this context word, do the words match? Is the context word really a context word, or is it a random other word? So to create this, we have to enter our two inputs into our embedding layer, and this is then the embedding layer has the dimensions vocabulary size by embedding dimensions. So in this case, it would be 10,000 by 300. Then we have two lookup tables to make the things faster. And from the lookup tables, we then get a target word vector and a context word vector. We combine these in a simple dot product so that we have two, it's not layers, but we have two ways the signal flows through the model, as you can see here. And to combine these two flows, we use the dot product, and then in the end we just have a sigmoid layer with one node, just to make a binary classifier. Is it a context or is it not a context? So this is the idea. Let's see how to implement it. And there's another thing. I added to this code a subvert encoder, because subvert encoder, we have already used them. They are very, very useful, but it's not so easy to train them. What is the idea about a subvert encoder? The idea is you will always have the problem that you might have words that are not in your training data if you try to analyze new texts or whatever. So, this is called out-of-back vocabulary. You have some words that are just not in the model, and therefore the model does not know what to do with it. A very clever approach to overcome this problem is the so-called subvert encoder, and there are different algorithms for this. The idea is that you can specify the number of words that you want to have in the end, but the algorithm will cut the words that you have into tiny pieces, like for example, unbreakable might be un and breakable. But it even goes further down to just the character level. So in the end, it's a combination of a character level model then and a word model. And this means if you have a word that is out of back vocabulary, that you do not know what to do with it, or the model does not know, then this word will be automatically divided into subwords, and in the end there should be no word that is really out of vocabulary. And we want to implement this. So let's have a look at the code. Yeah, these are the normal libraries here. As you can see, I already uploaded it on GitHub. We take the normal libraries, and you also have to install sentence piece. We need this for the subvert tokenizer. The whole sentence piece approach will be integrated directly into TensorFlow text. TensorFlow text is an additional library in the TensorFlow framework, and it's quite useful. But now sentence piece is not fully integrated into TensorFlow text, so you should install sentence piece. Okay, then what we are doing here is we just take a huge txt file. In this case, I take a collection of poems, English poems, and I want to create my Word2Vec model on these poems. Then we have a vocab size. Vocab size is in the model later the number of different words that should be used training the model, and these will be, in this case, the 10,000 most common words in our text. But words are not just words, but words are already subwords then at this point. So we have to define how many subwords we want to create from our text, and I went here with 15,000 subwords. Then we have a parameter that is called window size. Window size means it's a window defining what is the context of a word. So this means we will go through all the text, and if we have a word, it is in the context with the word after this word and after this word. So we have a window of 3 words altogether, but you can change this, of course. Vector dimension is the dimension of the vector space later, and in this example I went with 768 dimensions, and these are the dimensions of the famous BERT algorithm. Next thing is epochs, and you might wonder, 1 million epochs, this sounds like quite a lot. It is quite a lot, and we will need a lot of epochs here. But the point, as we will see later, is we have a batch size of 1. This means in every iteration, we just take one pair of words and try to evaluate it. So this is the reason why we have a huge number of epochs here. Okay, these are just parameters for the validation of the model here, and we will talk about this later. So first, what we are doing is we read our file. Then we have a function to build a data set, and this function will return our data, a count, a dictionary, and a reverse dictionary. So the data is our words, our sentences on which the model should work. The count is which word appears how many times, and then we have the dictionary where each word is just mapped to an integer, and a reverse dictionary that you can use to look up the integers and then find the words. And then we take the sentence piece library, and there's a trainer function. So this function here trains now a subword, a specific subword tokenizer. And as you can see here, it takes the file name and our subsize, this number of subwords that should be in there. This has to be trained first, and then we have a model. You can load the model. You can test the model here. And now we create our vocabulary. And this function here is breaking down our text. Text is this collection of poems. Is breaking this text down with the subword tokenizer in different tokens. So in the end, we have one large list with as entries not the single words but our subwords, but in the same order as the text was. Okay, now we create our data, count, dictionary, and reverse dictionary. We create a sampling table. This is a lookup table, so it makes it faster. And the cool thing is this is already defined in TensorFlow Keras. The same is true with the skipgrams. What is a skipgram? Now we have to create, we want to use negative sampling. This means we want to have pairs, and many of these pairs are real context pairs. This means which word comes in, with which other word together in this defined window of 3 words. And to create this, we create, we use the Keras preprocessing sequence skipgram function. And this is exactly what we want. So we have here then a couple, and a couple contains a word target and a word context. So these are our words that on the one hand, all the words that are in the dictionary, and on the other hand, word context, all the words that are in this window of 3 words in the original sentences. Okay. Next thing is we create some variables. We create an input target and an input context variable. We have to do this because now we are not using the Keras sequential API, but we are combining different layers. And we can do this, as you can see here. Here we define an embedding layer. It's just a Keras embedding layer, and it gets vocab size, vector dimension, and input length is 1, and it has a name, embedding. Now we define our target, and we say target is embedding, and embedding is connected to input target. Then we have to reshape our layer so that the dimensions function, and we do the same with context. Now we need the cosine similarity. because the similarity will be the output in the secondary model in our validation model. So to define the cosine similarity, we can just take the Keras layers dot function, because this is what it does. Cosine similarity is nothing but dot multiplication of the two tensors. And as inputs, we have target, and context. We have to specify the axis. And we say normalize true. This means that the cosine distance, that it is the cosine distance, so it has numbers between 0 and 1. Okay, again, we perform the dot product operation to get our similarity measure here. So we have to reshape the dimensions again. And this is then our output, where we just add a normal dense layer with a sigmoid activation function. So this is for our binary classifier. Is this a context word or not a context word? And now we can create our model. It's a TensorFlow Keras model. And now we specify what we want to have. We want to have the input. This is input target and input context, and the output. And everything else is already defined, because our input is connected via target with the output. Okay, we take the binary cross entropy loss function, and in this case the RMS prop optimizer. Then we create a second model. This is our validation model. And for this validation model, so the problem is we want to find out, is our model really learning something? And this is not so easy to do. I will tell you something to this a little bit later. But to create this model, we create a subclass, a similarity callback class. And in this class, we run similarity call. And this means now we are testing the vector that we have for a word. So our model will create a Word2Vec vector, and now we take this vector and see what are the other words that are closest to our word that we want to validate. And this is what is happening here, and in these two functions. So this function just runs our similarity call, and here we get the similarity, and the similarity, as you can see here, is that we, from all the cosine distances that we have for all the words of the vectors, we take those with the smallest distance. But it means also that we have to run this over the whole vocabulary, and this will make the process quite slow in the end, or slow it at least a little bit down. So if you want to have a faster learning model, then you probably will change some parameters later in the running. I will come back to this. So, okay, and what are we doing now? We have our count. These are the 1 million epochs that I specified here. 1 million epochs, and now we just go in a for loop through all the epochs. In each epoch, we have our 3 arrays here. One is for the labels, then we have the word target and the word context, and we have our loss. This means we train our model, but it's really, as you can see here, it's batch size 1. So we really just take one argument and then calculate the loss, and every 100 steps we calculate the loss, and every 10,000 steps we run our simulation to see if the words that are said to be similar in context, if this makes sense or not. Okay, then what we want to have in the end is the weights, because the weights of our model, these are our Word2Vec vectors in the end. So we have to store them. Here we just print the shape of the weights, and we store them in a way that we can open them later on in TensorBoard. So we have to create a meter and a vex file. And now what we are doing is we save for each word the weights as our vectors and the labels as our meter file. Then we close everything, and this is it. If you want to see how these vectors look like, you just can open project.tensorflow.org in normally any kind of internet browser. Yeah, so this is what the code does. And what else should I add? Well, as I already said, it's quite a good approach, and it's very fast. But nevertheless, training your own Word2Vec vector space will always take a lot of time. For example, in this case, with 1 million epochs, it took me on my machine 2 days to run the code. So it's a GPU enhanced laptop that I used. It's not the best thing that you could use probably, but it's not so bad. It took 2 whole days to train this model, and you will notice that if you look at the loss, the loss behaves very, very strange. It's not decreasing all the time, but this is due to the point that we have batch size 1. So if you look at the loss, the point is what we get is just the loss for 1 pair of words, and this is changing all the time. What you want to see in the end, and in this setting I have here 1 million epochs is not enough for this. What you want to see in the end is that the loss goes down to 0 most of the times, because this means that your model is capable to really predict if a word is in the context of another word or not. As long as the loss is not 0 most of the time, you have not trained the model enough. So it's really quite demanding for the computer to do this. Hope you like it. There are many things you could add to this code. For example, there is no automatically saving of the model and the weights. So if you shut down the computer, everything is lost. There is no way to start a pre-trained model again. These are some very useful things you could add. And of course, you can try and see how it works. And let's have a close look in the TensorFlow, TensorBoard thing, how this looks in TensorBoard. So as I said, we just take projector TensorFlow, open it into a browser, and here we have our vectors. So we have our vector. No, these are not the right vectors. First, we have to load the vectors that we really want to have. But this just now I would have to specify the file, the vex file and the meter file. Here's another vector space loaded, but it's in the end it's more or less the same. You can specify if you want to have it in a 3-dimensional way or in a 2-dimensional way, and then you can see here, for example, which word is in which context of other words. And you will get here, for example, in this case, the 100 words that are closest to our word meter. You can search for words and see what is happening there. Okay, I think this is quite nice, and this should work for you, probably. As I said, I hope you like it. And yeah, work on this code, try to enhance it, try to test it out. Perhaps you find a cloud server where you can run it, or you just take a small txt file with not so many words, and then you will see how this whole concept of Word2Vec works in the end. Okay, see you soon.